Hello and welcome back to Electronics with Emrys. In this video we're going to be taking a closer look at this circuit that I found in a previous video where I tore down a soldering station. If you'd like to check out details of where this circuit came from, you can take a look at that video that I'll link at the top of this video. The purpose of this circuit is to take the sensor resistance that's over here connected between Con 4 and Con 5 and amplify that value up to a number that the MCU can read in very easily. Our microcontroller was running off of 5 volts, and that's going to mean that the ADC in there is referenced to 5 volts. I don't know if this microcontroller had an 8-bit or a 10-bit ADC in it, but regardless, you're going to want to have a voltage that runs across as much of that 5-volt range as you can to have more detail and better response of your system. This sensor is only a few ohms. So the voltage divider here between a 6.8K resistor and a couple of ohms down here is going to be a very small number. The 220 ohm resistor provides a little bit more shift to put that voltage up at a higher value, but it's still going to be a relatively small voltage, so in the millivolts. And we want that to be amplified up to something around maybe 3 or 4 volts, and that'll make it easier for our microcontroller to read it in. This circuit converts the resistance of the temperature sensor up to a voltage at this output node. We know just from looking at it that there's going to be a relatively small voltage at output because there's only 220 ohms down here, while there's 6,800 ohms up here. So the voltage divider is going to result in a small percentage coming at the output. Let's go ahead and run the simulation and see what we get. So here you can see that the voltage varies from around 157 millivolts up to around 225 millivolts. This is perfectly linear, and that's because it's a voltage divider and it just depends on the resistance value. And in my circuit, I'm varying the resistance value through a PWL statement from approximately 0 ohms up to 100 ohms. We're going to have an input voltage going into an op-amp. And for the sake of this, let's go ahead and just call this R4, and that one R6. That's our V out, and maybe we'll name that V out 2. This is a classic op-amp circuit with a non-inverting gain. For the analysis of the circuit, you need to know that there's no current flowing into the inputs of an op-amp, and the output can do whatever it needs to in order to keep these two inputs at the same voltage. That is, of course, assuming you have negative feedback, which we do in this case. So if we put in an input voltage here, and these two pins are the same voltage, then this will be the input voltage also. And since no current flows into the input here, then all of the current through this resistor will also be the current through that resistor. We're just going to label the current here I. And we can determine that I is equal to V in divided by R6, just from Ohm's law, with the voltage in being across this resistor and the current being I there. To find the output voltage, we just add up the voltage of this resistor plus the voltage on this resistor. So output voltage is going to be equal to the sum of I R4 plus I R6. But actually, we already know what IR6 is, because I times R6 is equal to V in. So this is V in. I is replaced with V in divided by R6. So we have V out equals V in over R6 times R4 plus V in. Now we can rearrange things a little bit, take V in out. And this is basically the classic formula for the gain of a non-inverting amplifier. We have that the voltage gain which is the output voltage divided by the input voltage, is equal to R4 divided by R6 plus 1. So in our case, R4 and R6, that's 3.9K and 6.8K. So that's our gain for the first part. This is just the standard non-inverting amplifier setup using the LM358 model so that we can look at a simulation of it. I'm plotting the output voltage and input voltage in a single plot, and then the ratio of those two, which is the gain. We expect to see a gain of 1.57. After running the simulation, we can see a couple of interesting things. First, the output voltage doesn't go all the way to 0. So even though the input voltage starts all the way down at 0, we can see that the output gets stuck at about 25 millivolts. And it stays there all the way over until the input voltage is around 18 millivolts. After that, we can see that the output rises linearly, same as the input. But on the gain plot, it's kind of interesting because at the very beginning, our gain is absolutely enormous, 240,000. And really, that's just because we're dividing by 0 essentially here. So our number shoots off towards infinity. So let's go ahead and change the scale here so we can get a better look at what's going on. So now we can see that once the device starts operating correctly, the gain drops down to about 1.57 and it stays there across the entire operating range. The way this shoots off at the start is primarily because the output is not related to the input whenever the input is below a certain voltage. We can look at this portion of the circuit also as a voltage divider and kind of ignore what's connected to the output of it, even though they do interact with each other. Let's just look at how this circuit works and what output we get. Similar to the sensor voltage divider, here we've got a large value resistance at the top of the circuit and a smaller value at the bottom. So we're going to see a small percentage. Looking at it right now, I'd say 2 to 3% of the signal is going to be showing up at the bottom because we have 100K approximately total, and then we have 2 to 3K down here. This voltage divider is used to provide the amount of offset for the amplifier, and this is used to calibrate the sensor for a specific heating element. After running the simulation, we see a very similar result to what we had on the other voltage divider. It's just that the value here is a little different. So we're getting between about 97, 98 millivolts up to around 145 millivolts max. Now I know that in my particular unit, it was tuned to have 500 ohms on this potentiometer. So that means that it's going to be running around 122 millivolts, and that's the value I'm going to use in the next circuit. Let's look at this portion of the circuit here. So we're going to have the same thing, V in goes into, so we have R9 and R10. So this is R9 and R10. So it's likely that you're thinking that this circuit looks an awful lot like the circuit we just did an analysis on, because they are practically the same circuit. The only difference here is that this is not ground. So whenever we do this analysis, we're going to be finding the current here. V in is going to be the same voltage here and here. And our output voltage, VO1, is going to be an amplified version of V in. So to find out the gain of this, all we need to know is this current so that we can find out the voltage drop across this resistor. So I is going to be equal to the voltage across R10, which is on this side it's V in, and on this side it's V minus. So it's V in minus V minus divided by R10. In order to get the output voltage, all we need to do is start at ground. So remember that we have a supply here, so we're going to go from ground to this supply, so V minus, and then we're going to add this voltage, which is going to be VI minus V minus plus VI minus V minus Then we're going to add this voltage, which is going to be I times R9. So now we know I is Vin minus V minus divided by R10. So we can set this equal to V minus plus Vin minus V minus. These two will cancel out, so we don't have to worry about those. Plus I, which is Vn minus V minus, divided by R10 times R9. We can rearrange this to put R9 and R10 together, so we have those as a ratio. We're going to have Vn plus Vn times that ratio, R9 over R10, plus V minus, that's minus V minus times R9 over R10. So we can combine together these two terms because they're both Vn's. So we're going to have Vn times R9 over R10 plus 1. So this is our standard gain equation, right? And then we're going to be subtracting V minus times R9 over R10. And since R9 over R10 is a gain, that's an increase, V minus is going to be increased by almost the same proportion that this value is over here. But this one is going to be increased by R9 over R10 plus 1, while this is increased by only R9 over R10. Now the important thing to remember here is that V minus is going to be a constant value in most systems. So now in the system we have here, it's going to be a little more complicated because we're not connecting to a supply here, we're connecting to a voltage divider. And this voltage divider produces different voltages depending on what the feedback is doing. So this is not as simple as the circuit I've drawn here, but this circuit gives you a pretty strong idea of how that circuit is going to operate. So this one is going to act a lot like this one, which means basically what's going to happen is our output voltage is going to be shifted by this amount. Now if we take our input voltage and assume that's going to be about 100 millivolts, R9 and R10 we know the values of. R9 and R10 are 220K and 1.5K. Let's say we don't know that value for now. So we're going to have V minus, we're going to have V out 1 here. And R9 over R10 is 146.67. So we're going to minus V minus times 146.67, and that's V out 1. So now let's assume we want V out 1 to be 0. So we're trying to tune this such that whenever our input is 100 millivolts, then our output is 0. So how can we tune that? Well, we just need to choose V minus to be the right voltage for that. So we're just going to rearrange. So we have V minus times 146.67 equals 0.1 times 147.67. And then we're going to divide both sides by 146.67. We just need to set V minus to be 101 millivolts, and that'll mean that our output will start from 0. So this output up here will start from 0 whenever this value is 0.1. This circuit is very similar to the other amplifier circuit we were looking at, except that it has an offset voltage. This 122 millivolts is what we got from our voltage divider, so I'm assuming that it's going to be totally stable. And obviously it's not really in the final circuit, and we'll look at that here in a minute. But assuming that it was totally stable, this is what we should see. Again, I'm plotting the output voltage, the input voltage, but now I'm going to be calculating the gain a little bit differently. I'm going to look at the output voltage divided by the input minus the offset. And after running the simulation, you can see why I did it this way. So the offset is going to choose when the output is going to start to shift. In my simulation, I set the input voltage and the time to be the same. So at 120 milliseconds, we have 120 millivolts on the input. As that voltage increases, we see that the output increases linearly at a very high rate. Now, the output gain does not appear linear, but we can see that it's around the range that we expect. It's about 157 right here. Now we can adjust where this offset puts us. If I just change this voltage to 0, rerun the simulation. With the offset voltage adjusted to 0, we can see that the amplification is the same as what we'd expect from the normal non-inverting op-amp circuit. It starts amplifying at 0, and then whenever it hits the rail, it flattens out. And our gain is 157 like we'd expect. So essentially what this offset is doing is choosing the minimum voltage for the input to start doing something on the output. Setting it to 50 millivolts, we see that we've just shifted the curve over to 50 milliseconds or 50 millivolts on our input. This circuit puts together all of the circuits we've looked at so far, with the two voltage dividers being on the left-hand side here, and the two op-amp circuits being here and here. The offset connection is right here, and let's take a look at this. Now, I've already run the simulation once, so we can see that the DC bias condition shows us 144 millivolts, so it's a little off of what we originally got, and that's because whenever you connect up this circuit, it's going to cause some additional loading. So you're not only looking at this voltage divider here, you're also looking at the output connection on the other side, which varies. So let's take a look at this whenever we run the simulation and see how it varies as the temperature changes. The green line is the output after the first stage, and the blue line is the output after the second stage. So we can see here that as the resistance increases on that sensor, the output voltage, which is out 2, is going to increase also. And you can see that the output is really not taking up very much of the range here. And remember, the purpose of this circuit is to increase the range, so the sensor is going to be able to be read much easier by the microcontroller. Of course, if we go into this circuit and we probe the actual sensor voltage, which is right here, then we can see that it has increased the range quite a bit. That voltage is very close to 0, and it barely changes by the time this blue line has changed a large amount. So we're looking at a few millivolts here at the bottom. That's changing to about half a volt here. Now, I would personally want this to have a much larger range so that we would be able to read a much more accurate temperature, but obviously that's not required in this product. It seems to work just fine with having only this voltage range. Adjusting the resistance range to a smaller value, so now our top end is only 10 ohms, we can see that it takes up a whole lot more of my plot area. It's a lot easier to look at now. And we can see by driving the resistance even lower, we're getting down to around 3.3 volts and up to the maximum of the op-amp, which is around 3.8 volts. Maybe the most interesting thing to look at in this circuit is the offset point here. So how much change are we putting on that input signal? So let's go ahead and adjust this value and keep the resistor for our temperature sensor the same. I'm going to set the sensor to be 2 ohms, and we're going to vary the calibration potentiometer from 400 to 600. Here we can see that the potentiometer value is varied from 400 ohms to 600 ohms. And interestingly, the output is on the rail, so it's not moving at all whenever we're at around 400 ohms. And it's not until we get past 430 ohms that we see the output start to dip down. So this means that if we had an input of 2 ohms on our sensor, that we'd be hitting the rail and we would not be able to measure that value accurately unless we calibrated the device down. So it seems that this sensor is very sensitive. Like, it's probably designed to operate between 1 and 2 ohms. So if we wanted to have our resistor on the input be 2 ohms, then we would definitely need to adjust the calibration down to have that be read properly by the ADC on our microcontroller. To be fair, this is a really cheap knockoff of a good product, so I can't really complain too much. This was an interesting circuit to look at and an interesting video to make. So if you're left with any questions, if there's anything you want me to look at further in this circuit, please post it in the comments. Let me know if there's anything else you'd like to hear about this, or anything that I haven't answered, or maybe something I made a mistake on. Feel free to post it. If you made it this far in the video, I want to say thank you very much for watching, and I hope you have a great day.